Hey guys, so today we're going to talk about power series, and even though power series won't be assessed, I still wanted you to be exposed to them and see what they are. It's kind of nice because it does sort of feed into some of the other things you learned about the Taylor polynomials. It's just an extension of that. So what I'll probably do is I'll actually probably put this into an ed puzzle, and there will be questions along the way that you'll answer, and then I probably won't have an extra assignment with it. Your assignment will be to watch this and answer the questions as we go, just because this won't necessarily be assessed on the exam, but it is still something I want you to kind of know, so I won't make you do an assignment on it. Okay, so just to recap, what I've done here is I've already created a fourth degree Taylor approximation using e to the x, so an approximation of e to the x with this fourth degree Taylor polynomial. Pretty easy to do with e to the x because it is its own derivative. So it was just, and at 0, if you're centered at 0, e to the 0 is 1, so the derivative was at 0 was always 1, and then I would just divide it by the factorial, right? In factorial. And so an approximation for e to the x becomes this. Now we know that if we continued to go out further, we'd get an even better approximation, an even better Taylor approximation for the e to the x curve. And I've done this before, but if I go to Desmos and start typing this in, let's do the function e to the x, and then let's do the Taylor polynomial 1 plus x plus, plus x squared over 2 factorial. See how that's fitting to the curve right through here? Let's pull this down some so we can really see that. If I put the next one in, x cubed over 3 factorial. Ooh, that's nice. Okay, let me zoom out too so we can see even better with a good scale there. I think we did a fourth degree and we had x to the fourth over 4 factorial, and that looks even better. Look how nice that is. It doesn't look like anything good is going to happen over here, but on the positive side, it's looking like it's really matching up there. So it seems to be doing all right. If I keep going, let me see, plus, okay, well, if I did another one, it'd be x to the 5th over 5 factorial, right? Okay, and so that one seems to be doing a little bit better. I mean, you see it veers off as I get up here. But this is a good approximation, and I'd imagine that if I could keep going out, it would get better and better and better. So, the power series is more about it's a series, it's an infinite sum. So the power series is about taking these approximations out to infinity. And it's not hard to see on this one that I could go on forever because there's a pattern to this. It looks as though plus x squared over 2 factorial. I can see the pattern fairly easily. I'm going to write it. I think you can too. Over 4 factorial. Remember, this is the 0 index, this is the 1, this is the 2, this is the 3, this is the 4, plus dot dot dot, plus x to the n, the index, right, over the index number factorial. That seems to be the general term in this series. So if I was able to take this Taylor approximation out to infinity, it becomes what we call a power series. A power series is some sort of polynomial, some like infinite degree polynomial. Think of it that way. It has an infinite amount of terms, it has an infinite degree, and it, instead of only approximating e to the x, it actually gives the value. It gives the same value as e to the x. So if I wanted to know what e squared was, for instance, that's just substituting in 2 for x. It would be 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial. You could just substitute 2 into the polynomial rather than into the exponential function, and it would give you that value. So if you take it out to infinity, it will converge onto whatever e to the x is. Now, not all power series converge to particular functions for every value. So it might only converge for certain values, meaning like it might only work for x values between -1 and 1. You can use this polynomial to get the exact answer of this function, but only for x values between -1 and 1. That's just an example. That's not the case here. So we are going to be looking at some different functions, like e to the x, some famous functions, e to the x, natural log of x, sine of x, some popular transcendental functions, those higher level functions. And we're going to be looking at ways that they can be represented by a power series. And sometimes, like I said, sometimes they will converge over for any value of x, and that means over the whole, the radius of convergence, the size of convergence, the number of values that the function will converge onto the series for. Sometimes that can be for any value. That would make the radius or size of the convergence infinite. Sometimes the function only converges to or has the same value as that infinite degree polynomial for certain values of x. This one here actually converges to this infinite degree polynomial, or has the same answer as this infinite degree polynomial, is equivalent for any value of x. And I want to show you why that works, and it's really more what we're doing in the next video. Determining like a radius of convergence. And when I say that, what that means is I'm looking at the size of the interval of x values. For what x values will the series converge, on how big is this interval of convergence. So this is what I'll do here. If I want to figure out what this series converges, for what x values this series converges for, I'm going to actually use the ratio test. We always use the ratio test to do that. And so I'm going to have the limit as n approaches infinity of x to the n plus 1. Remember, you do the n plus 1th term, so you replace all the n's with n plus 1's, and then you divide it by the nth term, which I'm just going to multiply by the reciprocal here instead of dividing by the n term. Okay, look what happens here. The x to the n cancels with this power here. This is definitely useful because this is going to be on the AP exam, just being able to use the ratio test. N factorial cancels with the factorial part of this and just leaves me with that n plus 1. So I have the limit as n approaches infinity of the absolute value of x over n plus 1. Now you're not used to seeing an x in these problems. You would have seen like 2 to the n over n factorial. You wouldn't have seen an x in there. So that's why this new phrase is coming out, radius of convergence. All that we're trying to determine is, for what values of x will this actually converge? Does it converge at all for any values of x? So we're just trying to play the game of what can you put into this series that makes this converge. And the radius of convergence is how big the interval is of x values that this does converge for. So I hope that that's clear. So what I would do here, well, I'm doing a limit as n approaches infinity. So n is the variable we're dealing with here. So anything that's not an n can be taken out of the limit. So I'm going to pull out that absolute value of x. Treating it as a constant because it's not the variable in question. The variable in question is n approaching infinity. That's the thing that's changing and approaching infinity. And then this becomes, well, this limit right here, if you put infinity in here, 1 over something really big, that's just going to 0. So this is equal to the absolute value of x times 0. Remember with ratio tests that the way it turns out is whatever you get after you've evaluated that limit converges. That should say converge. Ooh, look at that, that's bad. Let's fix that. Converges when the limit is less than 1, right? Well, this is the limit, absolute value of x times 0, and this is going to converge, this black series that I wrote up here is going to converge when the absolute value of x times 0 is less than 1. Well, y'all think about that. Couldn't you put anything in for x and multiply it by 0 and it'd always be less than 1? So our radius of convergence is infinity. And what that means is that x can be anything, and ratio test says that the limit will always be less than 1. So no matter what I put in here for x, this series always converges. So if this power series always converges, and this power series can be, which, that's this is x to the n over n factorial, this thing I was just showing to you, this series that we just checked the convergence of, it always converges for any x value, no matter what you put in there. So next time you see a 3 to the n over n factorial, you automatically will know, yes, it does converge. And we did the ratio test to prove that it would work for any x value. And not only do you know that it does converge, but you know that this is the series, it always converges to e to that number. So if I gave you the series, let's do x to the n over n factorial. This is e to the x, right? It is also just this series that I've listed out right here for you. Those are all the same thing. If I asked you, for example, if I gave you this and said 2 to the n over n factorial. If I gave you this and said, does this converge or diverge? Well, you'd have to probably prove it, especially if it was on this year's AP exam, where you're going to have to, definitely justify yourself and explain your reasoning. But I know that this converges. I could do the ratio test to figure that out, and do the n plus 1 term and the n term and all that stuff. But I know it converges because now I'm recognizing that, oh, this is just an x to the n over n factorial, where x is 2. So this is converging. And not only do I know that it converges, but because it's this special power series, I actually know what it converges to. This sums exactly to e to the x, where x is 2. So I know what this big old thing adds up to. So it would be 1 plus 2 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the 4th over 4 factorial. This thing converges or adds or sums exactly to e squared. That's what it would equal to. So before, we were just kind of telling if something did converge or did not converge. We didn't say what it would add up to, unless maybe it was geometric. Now, if it is a special power series, one that I can kind of recognize, now I can see that it converges because it's of the form of the e to the x power series, and I know that it converges to e squared. So that's what power series are good for. Here are a few that I wanted to look at, for instance, let's look at this one, and let's just see if we might graph them to see if we recognize them. These are actually some ones that are they should look kind of familiar to us when we look at their graph, but this one already looks, it's got that x to the n over n factorial going on, so it looks like it has that e to the x piece to it already, just from the previous example we were looking at, but it's got an alternator on it. So I don't know what that's about or why it has that in there, but it's sort of like this. If I rewrote this series just using some, exponential rules, negative 1 to the n and x to the n, that's the same thing as negative 1 times x to the n over n factorial, right? I mean, that would be because you would still multiply, or you would still raise both of these factors to the value of n. And so that's the same thing as negative x to the n over n factorial. So all they did was take the e to the x power series, which we just learned on the previous page. The e to the x power series is this black series right here. This is always going to be e to the x, x to the n over n factorial. They just took it and they replaced the x with negative x. So this bad boy is just e to the negative x. That's what this thing is. Okay, let's look at the next one. This also has an alternator on it, and then it's got x to the 2n over 2n factorial. So what I'm going to do is I'm going to pause the video and I'm going to list out a few of the terms, and then we're going to graph it and see what it looks like. Okay, so what I did here was I went ahead and listed out a few of the terms of this series, and so I'm just going to write the little index number below it so you'll know what I did. Here I substituted 0 in for the n values, right? That's all I did, just plugged in a 0. Then I plugged in a 1, then I plugged in a 2, then I plugged in a 3 for the n values, and I got those terms. I'm going to go to Desmos, and I'm going to graph that series that I've listed out there. Let's see, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Oh, ha, no, why? Okay. And I'm going to keep going, and I'm just going to see, because I can already see a pattern to it. It looks like it's alternating, and it's got even powers. Oops. And what I'm trying to do here is I want you to look at it and see if you can determine what this is eventually going to sum to as I go out to infinity. Because I can keep going with this if it's an infinite series, and I'm going to zoom in on it. And I'm hoping that you can kind of see what it looks like it's modeling. Oh, Control C. Okay. Plus x to the 12th over 12 factorial. This to me, I mean, it's not, you know, I'd have to go out several more terms, but this to me, and I hope that you can see it too, looks like a very familiar function. It looks like cosine of x, right? Do you see that? Here, I'll take it away. Look, definitely looks like it's trying to match the cosine function. So it looks to me that this is the very special power series for cosine of x. Okay, this one, if we did this one, I'm going to go ahead and list out the terms for this one, and I actually think you've seen this one before. If I put 0 in, I would get x. If I put in, that's for my 0 index, if I put in an index of 1, it's going to alternate because the 1 is going to make that negative. 1 would make this x cubed. 1 on the bottom would make that 3 factorial. It's kind of looking like it's going to do the same thing that the other one was doing, but just with odd numbers. Like it's alternating, but it's got odds. And like I said, I'm pretty sure you've seen this one, and you probably have a really big hunch about what this one is doing, but I'm going to go ahead and do the same thing on this one. So it's x starts with x, and then it goes x cubed over 3 factorial, and then it goes x to the 5th over 5 factorial, and then it was what, 7, oops, come on, you can do it, and then it was 9, and then it was 11, because it was going odds. It was 2n plus 1, it was making odds. And look at that guy. That looks really periodic. That looks like sine of x, right? We've seen that one actually in another video somewhere. So my point in doing this is just to show you that there are these very special series, infinite series out there that are basically, I want you to think of them like infinite degree polynomials, and they do fully approximate these very special functions that we know, and sometimes they do it over for any x value. Sometimes the radius of convergence is any x value, and sometimes it's only certain x values. So here is the way this can go down. This is important to know. A power series centered at C, because remember they can be centered at different places. All of these are centered at 0, by the way, because they're all just x. If they were like x minus 1 to the n or something like that, they'd be centered at 1, right? Those are different centers, but all of these are actually Maclaurin series that you're looking at here. So, but this is how this works. There's 3 different possibilities for how a power series might work. A power series might converge absolutely for all values of x. That's what e to the x did. We looked at it, we kind of, analyzed it with a ratio test, and we determined that no matter what value of x you put in, it will converge, and it will always converge to e to the x. And then there's this blue case, which is honestly the most common one for most power series. There exists some radius, some interval, some value greater than 0, such that the series converges absolutely for x minus the center less than r. So within a distance r away from c. So basically what that means is that your radius of convergence, for instance, let's say that a power series, I told you that a power series only converged on the interval -1 to 1. If it only converged on the interval -1 to 1, that means that only for the values in between -1 and 1 will that power series approximate that function. And if that's the case, think about how large this interval is. That interval, well, just think of a number line, y'all. That's all this is. These are just numbers. That distance is a distance of 2, right? 1, 2. So if you think of this like a circle of convergence, then the radius would just be 1. So if the interval of convergence was from -1 to 1, the radius of convergence, which is what this capital R is, the radius of convergence would just be 1. And so then the third case is that the series might only converge at x equals c. And that's kind of a boring case. That just means that the function and the series only have one thing in common. It would only approximate and give the right answer at the center, which is kind of what Taylor polynomials do. They have that one point in common, and then from there they approximate. So most of the time you're going to be looking at these top two as possibilities for convergence. Okay. So I kind of wanted to look at this just to see, let me see if I can move everything. Okay. This says if the absolute value of x is less than 1, then the blank series formula assures us that this power series is equal to this function. So I want to see if you can help me with this. We're going to try to come up with that. Look at this power series. Look at these values. If you were to look at these and say, oh, okay, how could I determine how to get to the next one? What's the pattern here? It looks as though you can get to the next one by multiplying on another what? Another x, right? So it has a common ratio to it. Oh, it has a common ratio, and it's of the form something to the n power. So that means that this is a blank series. And that would be a geometric series, right? This is a geometric series. And its common ratio, the common ratio, the thing that you have to multiply by to get to the next term, is x, right? Because you'd have to multiply on x to get to the next term. If that's the I keep putting ratio. Okay. If that's the case, then the function that this converges to, the thing that it sums to, remember that a geometric series always converges to a over 1 minus r. So then the function this converges to should be a, the first term, this guy, over 1 minus r, which our common ratio here is x. So the function that this converges to is 1 over 1 minus x. You got a rational function there. So 1 plus x squared plus x cubed plus ... always converges to the rational function 1 over 1 minus x, but only for values, because even the geometric series, we said that a geometric series only converges for the absolute value of r less than 1, right? So that would be for the absolute value of x less than 1, correct? And so this only converges for absolute value of x less than 1, which is numbers like, absolute value of x being less than 1. That's technically the same thing as between -1 and +1. right? And so it's only going to converge for values like 1/2 and 1/3 and -1/5, those kinds of fraction values, which totally makes sense because if you thought of like, what if x was 2? 1 plus 2 plus 2 squared plus 2 cubed plus 2 to the third plus, no, that's what 2 cubed is, plus 2 to the fourth plus 2 to the fifth and so on. That just continues to grow and get bigger without bound. So that wouldn't converge. But with these fractions, between -1 and 1, it does have more of a feel of convergence. Now I can figure out exactly what number it converges to because I can substitute it into this function that this power series converges to. Okay. All right, so this is the general form for a power series. This is sort of summing it up. An expression of this form where you have a constant plus some coefficient times x plus another coefficient times x squared plus dot dot dot, just basically a Taylor polynomial that goes on forever. And it's centered at 0. If it's not centered at 0, this is the general expression for that, and it's just x minus a, where a is the center. So a power series is basically an infinite degree polynomial, very similar to the Taylor polynomials we were looking at. It just goes on forever. All right, and this, again, this is just sort of wrapping up what we talked about earlier on the last slide, so I don't really have to say much more about it. It just says the geometric series is a type of power series. It is centered at 0, and it converges just on -1 to 1. So we know that this does equal 1 over 1 minus x. Okay, so I'm going to stop here, and that's your power series notes. I'm hoping that this was uh, not too painful, and we're just going to continue on with talking about, some different power series tomorrow, and, radius and interval of convergence too.